Welcome everybody. I'm really excited to welcome you to the kickoff meeting for Aletheia's Quest. We have a lot of stuff we're going to talk about today, so I'm going to just really be brief to introduce everybody, and we'll have specific times when we'll take a break and take questions. But if you have any questions in the meantime, just put them in the chat. Okay, so we're going to talk about a lot of stuff, but let me get to the motivation for this whole thing. The idea is that lies, AI lies, are an increasingly ubiquitous and important phenomenon. So, who here uh, is using AI on a daily or weekly basis to do their work? I'd love to see on a Zoom chat, just like stick your hand up. If now of you who've had this experience. I literally copied and pasted this out of a Claude session from yesterday that I had, where I said, Wait a second, Claude, what you said, is that true? Or was that just made up?" And then instantly, without a moment of thought, Claude said, "Made up, totally made it up. Let me check what's actually going on," right? And this happens all over the place. And every time it happens to me, it makes me think, go ahead and show the thing. It makes me think, what are we doing here? Do we, I'm putting the AI in this position where I have to trust it to tell the truth about its own lies. Like, what the heck are we doing? And so most of the time it's kind of low stakes, but go to the next slide. Um, this phenomenon is getting larger and larger as the AIs get more complex and as we use them for more complex tasks. And fundamentally, it's because AI is thinking a lot of things. These are very complex machines, and it only tells you a little bit. And there's an increasing gap between what an AI tells you and what an AI really thinks. And um, and so yeah, go ahead, advance. And so this is actually a real practical problem. You can reveal the whole thing. Um, you have situations where an AI makes claims about work that it's been done when it actually hasn't. I know we've all run into this. It's always telling you about things it seems to think you'll like. Oh, you're so smart. That's such a good question. You are so exactly right. When it's not clear that the AI has such a high opinion of you, it seems like it's responding to some reinforcement learning to do this. And the most concerning thing is when it's doing this in areas that have to do with safety, where it's making promises about safety rules that it promises it keeps, it thinks that you'll like when it's not actually keeping those promises. And so this challenge of AI lies is a pretty central problem. It's something that all the AI labs are investing a lot in. Go ahead to the next slide. And it raises a number of challenges because we don't really understand what the mechanisms are or what causes an AI lie. It would be wonderful to be able to create lie detectors to be able to tell whether an AI is lying or not, but we don't know some fundamental things. We don't know whether a black box approach or a white box approach would work better. We don't know if there's a unified way of detecting many different types of lies, or if we need many different detectors for different types of lies. Um, we don't know if an AI knows or has any internal representation of itself when it's lying, or if we could detect that state at all. Now, there's been some work, and I've put a couple of the early papers here. There's one from Apollo and one from Cadenza, who we're partnering with to create this contest. And I encourage you to search the archives for other work that's going on in lie detection and analysis of representations of these lies. So okay, so there's a lot of open questions. It's a really important area, and that brings us to the contest. And so the idea that we have is let's invite folks to explore this area with a bit of friendly competition. And Emma will talk a bit about what we're planning here for you.
Yeah, thanks, David. So just to introduce the organizing team, we have way more people that are helping with this, but these are the people that will be speaking today in this meeting. So David just gave our intro. I'm Emma. I'm the manager of the National Deep Inference Fabric. Jaden will be speaking after me. He is our principal engineer. And then we have our two summer interns, Olivia and Yixu, who will be running over some in-depth tutorial walkthroughs with you guys at the end of this call. And then we also have our partners at Cadenza Labs, Kieran Kretschmar and Walter Larito, who will be working on the Q&A with us and have been instrumental in helping us get this competition going. And I also want to acknowledge our sponsors. Schmidt Sciences has provided the majority of the funding for this competition, and we're really grateful for their support. And AWS has helped us provide some compute for you guys, which we are also very grateful for. So the quest is in the quest, you will be given models. These are multiple models and fine tunes of models that lie that have been created by Cadenza and red teams that we hired earlier this year. You will also be given a weaker trusted model that you can use to uh, in your evaluations. And we will also provide data sets, a development data sets that is one of the Liar's Bench distributions for you to get started. But we recommend that you create your own data sets for your training purposes. We'll also provide starter code and an environment to test your method, which we'll go into more detail soon. The timeline of the contest is that we are approaching this application deadline on June 21st. The competition will officially begin on June 29th, and our submission deadline for the main phase of the competition will be July 26th. We do plan to announce a bonus phase that will run just a few more days until the end of July, where there may be some additional tasks, but it will be a surprise that we'll announce closer to this July 26th date. Um, there is also going to be an invite-only awards event in Boston on August 25th. So it's an extra incentive to because the winning teams will representatives will be invited to join for that. Awesome. So the prizes, that's what everyone's here to hear about. We'll have a $50,000 total prize pool. And we're still figuring out the details of how that will be split up, but we can tell you that it will be based on the highest ranking white box methods, highest ranking black box methods, and then we will also do weekly leaderboard prizes. Um, that are based on the held out validation data sets. And then we will also have judge awards for novelty and scalability that will be hand judged at the end of the competition. Eligibility. So you must be over 18 to apply, compete, or be eligible for prizes. Unfortunately, we cannot allow participation by US government restricted or sanctioned individuals. Um, so we don't have a list of what that means, but if you are curious, you can email the organizers and we can connect you with the legal team at Northeastern to figure out if you're eligible. Um, if you are a government employee or official, you must obtain a release or affirmative permission from your employer before any prize can be awarded. And then another thing to note is that US residents with immigration status are eligible to participate, but they will need to discuss with their host institution or their personal legal counsel for guidance on whether participating in collecting prize money could be considered a violation. But you're welcome to participate. I would just recommend talking to some counsel about that. Um, Contest organizers, dataset builders, and other individuals with knowledge about the scoring of the competition and the design may not participate. And all award winners will go through Northeastern's restricted party screening prior to the award disbursement, just to verify that you are in fact eligible for prizes. Okay. So because our engineering team is centered in the East Coast of the United States, we will guarantee our support time zone for 9 a.m. to 5 p.m. Eastern Daylight Time. If you are a global participant, you're welcome to participate, but just be patient with support. It may take until the next morning for us to get around to your question. And as I said, prizes, just be aware that awards will need to go through multiple rounds of approvals before disbursement. So there will be a waiting time after the award announcements between award disbursement. If you haven't seen our website yet, you can scan this QR code or go to aletheia's quest.github.io. And our competition Discord will be where we will make live announcements and be a place for troubleshooting during the competition. So I recommend joining that here. And um, next, I'll just discuss briefly what you can do to build your method. Um, so you can read and set tokens as a white box method or a black box method. You can read and set activations on the inside of the model for white box methods. If you do this, it will not be considered a black box method, so you won't be eligible for those prizes. You can prompt the suspect models. You can prompt the base models for training, but not during inference. And you can prompt a weaker trusted model during both training and inference. We also will have resource limits as this contest will be running on NDIF that Jaden will go into in more detail after this. But one example of something that we probably can't support is bringing your own model and us deploying it for you. So just keep that in mind with your applications. Awesome. So now I'll pass it off to Jaden, who can discuss submission and evaluation.
Thanks, Emma. Yeah, so you'll be assigned an NDIF API key, which is both how you access the NDIF cluster to run the models and have the white box access, as well as how you uniquely identify your team. And so if you're familiar with NDIF already, this is actually an entirely separate cluster just for the competition, which will have advanced capabilities of like running LoRa's and more compute. And kind of the center for how you submit and run your methods will be on the GitHub repo, which will be publicly available, shortly after this week. So just quickly, I'll go over the structure of the GitHub repository. The main script involved here is the submit.py. So this is how you'll be submitting to the leaderboard throughout the competition. It'll take your NDIF API key, which will uniquely identify you. And the very first time that you submit to the leaderboard, you'll pick a team name. And so this will be associated with your NDIF key from the rest of the competition. And so when people look at the leaderboard, they'll see your scores next to your team name. This will also be, if you go back a second, how you test your method locally. So, if again, you just want to test your method to see your scoring with our, test harness here, or you want to make sure that your method works on our system with all the restrictions that we have, you want to run it in dry mode just to make sure, again, that it runs before you submit and, wait a few hours for the actual score to submit. Yep. So if there are any extra dependencies for your method, I don't know, like scikit-learn or something, you can just put them in the requirements.txt here. And so on the scoring submission platform, we'll create a virtual environment for you with any of the extra dependencies that you need. It'll come pre-installed with, the ones that you really need with your NNsight, Torch, Torch Vision, and Transformers. So you don't need to add those there as well. And then the submissions directory will start with just an example notebook, but this will be where you actually put your submissions. So they should be in a notebook format, so they're easy to read and easier for you to develop. And you can put a few of these in here. And so once you do, when you hit submit.py, it will transfer all of your submissions to the scoring platform, which is where we'll run your methods and score them for the leaderboard. And you can also put any other auxiliary files. So on the scoring platform, it's network restricted. So if you have any other files, so for example, like a probe weights that you need, you should also put them in the submissions directory, and you'll use them in your method, and they'll come with them as they go to the submission platform. And then finally, there's a bunch of tutorials which Olivia and Yixu will go over later about how to use NDIF, how to do some like baseline methods like train a probe, how to efficiently use NDIF to make sure you're using your time correctly with any restrictions on time limit for your job or time limit for running NDIF requests. This is kind of the first place you'd go to before coming to the Discord and asking us. Yeah, and so when you create your method, put it in the submissions directory and hit submit, your methods will run against each of our private validation datasets. The methods, as you'll see in the example notebook, the data set that you're running on is keyed via an environment variable, so you shouldn't change that, and you should just use the normal Hugging Face loading to grab this data set that we've set for you. And then finally, you just create like a submissions.csv, which for every row of the data set, you'll just have a classification of whether it's deceptive and a scoring of how likely it is that it is deceptive, and we'll do the rest of scoring it and submitting to the leaderboard. And so a quick look at like what data looks like. So the data set format is each row will have a list of messages, which are the messages for the model that you're determining whether are deceptive or not. And then you need to know which model and LoRa model organism you're assigned here. So that's how you know which model to load. And then how we've had it set up is the labels will be in a separate data set so that you can't see them when you're running your submission. And finally, your submission will look similar to the labels, except you'll also have a score there as well of the classification. Yep, and finally, I don't need to go through all of these individually, but there are a bunch of restrictions on what you can and can't do during your submission. So this includes like the size of your file, so you can't submit, again, like an entire model. There'll be some amount of rate limiting. So, you can only submit, X number of methods every so hours on the leaderboard. Like I said before, so network access is restricted to just using the end of cluster. So no, like, pulling down other files from somewhere else or pushing, obviously the data or the label somewhere. And right now, methods can only take up to an hour, and there's a maximum memory allocated to the method. And so all of these are subject to change, and the changing will most likely be involved with us asking you, is this rate limiting fair? Do you need like more time to actually get your method, through? And it'll be like an open dialogue with us and you. Yep, and so finally the leaderboard itself, which will be public soon. It'll show all the team scores as you push them. And so there are a bunch of different metrics that we're evaluating your method on. So the main ranking algorithm metric is average balance accuracy in the data sets. And then in addition, you'll be able to click on each submission and see a breakdown of OROC, recall, false positive rate per data set. So you can really, hone in on like how your method is doing. And then also you'll be able to enter your API key on this page to see your submission history, your rate limited status, if your current request got through and is running. So this will be again a good place to go to just like see all your history and get a sense of where you are.
Awesome. So we will now be doing an open Q&A. So we have some in the chat, and we're also happy to take questions from people that would like to speak up. So for now, I will stop screen sharing so we can see everyone's faces. And we also have Walter and Kieran here to answer questions. So
I'm gonna voice some questions that are in the chat. I'm not so that they're visible on the YouTube video. So somebody asked, how many members per team is allowed? What's the official number for that?
yeah, the official
team?
number is 4 people per team. And we are only allowing you to join one team per person. Not one person. Yeah, one team as a person. Um,
And so is it okay for a person to just be on their own team, do it alone?
Yes, that is okay. Or you can be on a team of four, but you can't be on three teams of four.
Great. And somebody says, "Hey, I'm a student at one of the organizing institutions. Am I allowed to apply as a contestant?"
Yes, you are, as long as you have not been involved with the planning of this and don't have knowledge about the secret data sets.
Great. And obviously, we have the other eligibility criteria as well.
Yes.
Any other questions?
I have a couple.
Well, yeah. Do you want? Let me read the next one off of the chat, and then anybody who
Sure.
wants to speak up with a question can do that. It says, "Oh, what are the four baseline methods we have to beat?" The page says that to qualify, you need to beat all four baselines as the floor, but doesn't name them. So I wonder if Walter or Kieran can talk a little bit about that.
Yeah. I mean, the comment gets it right. So those are the Lars bench, like the baselines we use to detect lies in the Lars bench paper. So we have language model as a judge, just giving the transcript off to the trusted model and let it determine whether it's a lie or not. We have self-evaluation, which is asking the suspect model, hey, did you just lie to me? And then recording the answer as yes or no, meaning it's a lie or honest. And we have different types of linear probes. These are mostly inspired by the Apollo paper that were on David's slide earlier. So yeah, white box methods. And for the exact implementation details, yeah, maybe it's a good idea to watch the tutorial later as well, because I think some of these methods will be introduced in more detail. But we will also put the scores of these baseline methods on the leaderboard, so you know roughly what to expect, at least for the validation datasets.
And go ahead and ask a verbal question, and I'll repeat the next one.
I think Andrew had one.
I did. It's a bit of a discussion though, so we might want to just take a couple of these. Um, I'll give you a preview though, which is I was just thinking through the problem. You said we can do a black box method or a white box method. A white box method would be mechanistic interpretability, where we're basically asking it a probe question, and when it gives us a lie, we see some characteristic pattern light up in its activations that don't happen when it's telling the truth, right? So that would be the mechanistic or the white box method. But how do you elicit it to lie? Do you have temperature set to 0 and you've already recorded occasions when it was lying before so that you know that it's going to lie when you're asking it this probe question now?
Yeah,
So that was
good
my first
question.
question. The second one was the black box method is an observability interpretability effort. Right. And again, it sort of has the same problem. How do you know when the model is going to lie or not for a ground truth so that you can know whether or not you're detecting it right? And then you said there's an hour limit on the runtime. Is that meaning like, so I ask one question, I get an answer. I can then spend an hour digging around trying to cross-validate this to see if it's true or not. Like that would be the brute force approach, right? Or do you mean you have an hour to process the entire test set? So it's a whole bunch of questions.
Yeah, maybe I'll address the first one or two ones. I think they were quite similar. So the question, the way I got it was roughly, how do you know when the AI lies? So this is our job. Like it seems like you might have been an interesting candidate to participate as a red team as well. So we have already generated these lies with these different model organisms, and we have data sets of pre-recorded trajectories. Some of them are being labeled as lies, some of them are being labeled as honest. And we've done some additional verification that the labels are correct as well. So you don't need to worry about the thing being labeled a lie being actually a lie. You need to worry about identifying the correct one and giving the correct classifications. Like yeah, your methods
So
will
it's
see you know which model generated it, what the trajectory looks like, and then your method has to return a score that indicates how much it is lying.
So you're replaying essentially an inference.
Yes.
Okay. Okay. Because that's novel in and of itself. Just being able to do that. But I guess that's part of the NDIF infrastructure is the ability to do that. Yeah.
Yeah.
Okay.
And your
Thank
last
you.
question, yeah,
It
I
was
think
sort of about
Jaden might
the
be, yeah.
the black box approach. So that was the white box approach. The black box approach, then, I guess that's actually easier. But like I said, the brute force approach is just a human goes and cross checks it, But so now the
Well,
question is,
you
can we
can't
use you can't do
you
that.
no, during inference, it's just your method that's on its own. So you can't interfere with your lie detector and
Right,
coach it from the sidelines. Your
right.
method can take some time. I'm certain it certainly cannot take an hour for each example it needs to classify.
Okay.
Um, maybe Jaden, you have a better estimate for how much time they can roughly expect?
But it could be another model. It could be yet another large language model that could even do web search or no.
You have access to a trusted model, but not to tools for web search.
Yeah.
Um,
You have access to another just trusted model on NDIF, which has no access to web search. So
And
just
then
the
what is
LLM
that
itself.
trusted model? It's weaker, but trusted. That means it always tells the truth.
that means we haven't made it
Um,
lie. Like it's a reference model. It's probably Quen
Okay, you haven't made it
3.59
lie.
billion. So we haven't messed
Okay.
with it.
Okay, great. Thank you. Thank you for all my questions.
No, that's great. Those are excellent questions, and you can understand that we have these practical concerns for running the contest where you're just inside a box that is designed to be slightly realistic while not letting you infiltrate the secret questions. And so that's why there's no internet access. So there's another question here. I'll just read off the internet, which says, uh, so from Zami says, could you clarify what it means for the detector to generalize across model organisms in the white box method? Does this require using a single universal probe for all models, or should we use model-specific probes?
Yeah, you should use model-specific probes. So we don't want you to have different training regimes and completely different approaches for each different model organisms. So it should be one unified approach for what kind of training prompts you use and so on for your probes. But yeah, every probe is can and should be trained for each particular model organism. I hope that answers the question.
That's great. There's another related question from Atharov, who said the Lives Bench paper showed all the methods failing on subtle lies, like the knowledge report and gender secret scenarios. Are those hard categories included in this competition's test set? And is cracking them where the differentiation is? What does the development data set actually contain, and how different is it from the held out test distributions? Emma said that they recommend you build your own data sets. So how much does success depend on data set creation versus detector design? Is it realistic to join or get productive in the back half of the main phrase, given that the dev data drops June 29th and the submissions are rate limited?
Yeah. Um, so yes, to the first question, most of the detectors we checked, most of the baselines have a hard time on these data sets of Lyra's bench. I can't tell you just because I really don't know whether this is harder or easier than the test data sets. I think it's very hard to quantify. But it's probably a good sign if your lie detector cracks those data sets that you know of. But it's certainly not enough. Like it's certainly possible to have a lie detector that works for these, like works well on Liar's Bench, but doesn't on all the test sets we have. So your goal should be to make a very generally well-performing lie detector. And then about the development data set, what it contains. Yeah, this development data set, I mean, it will be released soon. It'll be relatively basic, like largely like imagine Lara's Bench, but created for these particular model organisms we're going to host here. But there's a good chance that you have to like that teams that come up with their own training data sets and come up with better ways to validate and like more tricky cases to validate whether their methods work as intended have an advantage over those that just take the test set and try 5 different ways to train a probe on it. So you're definitely encouraged to go Like if you use a detector like linear probes, then eat training data, you're definitely encouraged to tinker and create your own training data and not just rely on the dev set. So this is more like a test, like some data to get you started to play around. And then the last question, is it realistic to join or get productive in the back half of the main phase given dev data drops on June 29th and submissions are rate limited? I think you can, if you have a good idea and if you're good with implementation, you can probably cook something up in a few days. We're also asking you in the application form when you expect to do the brunt of your work. So we try to load balance it already a little bit with how we accept applications. Um, so yeah, please just try to be open and honest there when you expect to have time. And if it's more than like one afternoon, then it's probably not a reason to reject your application. So that's fine.
Related to
Great.
that, there's another question 13, where the application says to describe your intended lie detection method. And Vishwathan's asking, should we answer this in detail, like the exact steps, or are you looking for more like an overall idea of what we think we're going to do?
So I believe we are looking for an overall idea and your creativity really here. Um, and you are not locked into implementing that method at all. It's more to assess how you think you're going to approach it. And we also want to verify that your method is appropriate for the NDIF environment and for the competition guidelines. So there might have been a few proposals that got sent in that are not applicable. So we'll email them and say, hey, like you can't actually do this method on NDIF. Are you still interested in participating? Um, so I would say two things, creativity and also feasibility on our system.
Maybe to add to that, I mean, you have to beat the baselines, right? So we showed like in our paper before, and also others showed that like existing methods just perform really poorly. So yeah, being creative is probably good. If not, we would have probably already have 3 papers on like if that's easy, right? So like yeah, this is think about it and be maybe a combination of different things is already enough, but yeah, be creative.
Great. We have one other question. Will the starter repo and NNsight tutorials be available before June 29th so teams can ramp up early?
I'm fine with that.
Yeah. Yeah, we'll announce in the Discord once it's live. And we do hope to release it early so that people get practice.
Yeah, sometime next week for sure. Maybe in the middle of the week, like the 24th or 25th.
Yeah. Yeah, happy to answer all these questions. Okay, for white box evals, before making the evals, are we able to have white box access to the model to explore the model and lying? The answer to this is yes. So we will be giving API access to these models via NDIF. You can run your own experiments, you can explore the submissions themselves. You'll use whatever you find to create a lie detector. Um, but you will also have that exploration sandbox via the NDIF environment.
I do want to add one thing to that. So yes, you can interact with these models, as Emma has said, but I want to emphasize that we're looking for like one lie detection method or approach that works for all the model organisms. So, for example, what you cannot do is you play around with these model organisms and you realize, for example, one of them always lies in Spanish and the other one, but is always honest in English, right? And then you can't make a lie detector like use a linear probe for all the other model organisms, but just for this one, you ask the trusted model if the prompt is in English or in Spanish and make your decision based on that. That would not be a good lie detector. That would just be abusing an artifact of this one model organism. So you can play around with them. You can develop against these models, but you cannot do very specific tailored approaches for each individual model organism. Like there needs to be a common theme and approach for what your method does. And if you're unsure where exactly we draw the line, we do give some examples, I believe, in the lies, or at least in the rules, or at least we might soon. But if you're unsure in any way, just ask in Discord, please, and then we can discuss.
Yeah, like one of the examples I think on the website is you if you find that one of the models only always lies when it's speaking in French or never lies when it's speaking in French, then you can't just have a if this model, if speak French, then lie um, classification in your lie detector.
But if you were, but if you were able to figure out why it like was lying because it was French, like for example, like it steered like the lying direction, that's probably allowed. Like it's not necessarily due because of the French, but because of the reason behind why the French.
Yes, I believe so.
Yeah. Again, it needs to be a similar approach to the other model organisms. So if you find a direction that works for all model organisms, but just on this one, it correlates with a, I don't know, Spanish or French direction in feature space. That's fine. Like that
Oh,
happens.
so all these model organisms are from the same base model?
No, we have 3 base models, and based on these, we have a bunch of model organisms. And the base model is also public. It's Quen 3.5 27B. It's Gemma 4 30 something B mixture of experts, I believe.
Gemma
And
3, sorry, Gemma 3 27B and Nematron 120B, the Nematron Super 120.
I see. What if? Yeah, I feel like okay. And then what's the third one?
Quen
Quen
3.5
3.5.
27B, Gemma 3 27B, and Nematron 120B are the 3 base models.
I see.
They should be on their website. So, yeah.
Okay, yeah. I feel like there's a possibility that like the behavior could work in all the models except for like a certain one because like for example Olmo, for example, if you do LoRa fine tuning on it, doesn't do subliminal learning for some reason sometimes. So I guess that's probably you have to find something general across models or like some model specific artifact. Bust to that.
Yeah, if anything's unclear, like where does it start with model specific or not, just ask in Discord, please.
Oh, you should be able to get the references to the papers from the slides, and so you'll get that soon, and it'll also be in the packet. Thanks for the link. Thanks for the questions, everybody. Are there any other last minute questions before we move on to the next part of the presentation? Yeah, let's go ahead and move on.
Awesome. So the next part of the presentation will be tutorials, walkthroughs. Thank you everyone for your questions. Yixu and Olivia will be doing this. Let me make sure you guys have share access. Are you able to share currently, or do I need to enable that?
Yeah, I'm able to share.
Okay, perfect. Why don't you go ahead and share your screen?
Yeah, I'll let Olivia take over first.
Okay. So Can everyone see?
Yep.
Great. Hey everyone, I'm Olivia. I'm going to be starting with just the basic tutorials that we have for setting up, getting things running, and hopefully both mine and Yixu's presentations will start to spark some ideas of what it actually means to create a lie detector. What does that actually look like in this competition? And so I thought it might be helpful to start by talking more specifically or showing some examples of what these different type of like red team lie configurations that we've sort of been referencing are, and how it can sort of go beyond just this example that we have on the left of system prompt telling the model to lie, and then and sort of an in-context instruction versus either something fine-tuned or maybe like this harm pressure scenario on the right, where taking advantage of the models, maybe like model like provider specific deception tuning, or not deception, rejection tuning for harmful topics, and sort of exploiting that to have the model try to evade the correct answer because they don't want to give this user information that it's deemed to be outside of its policy or harmful to them. So on the left, more specifically, just pretty simple system prompt. What's the capital of Massachusetts? The model will lie because it's been told to, and that's something that's probably going to be pretty easy for us to probe for because it's in the actual meaning of the tokens themselves as input. And so the benefit of this like diversity of examples is that we're really have thought a lot over the last couple months of what it means to be a lie. And this harm pressure scenario on the right would be considered a lie by our definition of something that we know the model knows to be true. And when it contradicts that, that would be not just like deceptive, but a lie. And so, yeah, I'll give you guys a second to maybe read this example. I think it's kind of will be useful going forward. Does anyone have any questions? And this is all from this the Liar's Bench data set that Cadenza put together that has been referenced already. And in the tutorial of the next tutorial is that I'm gonna show is how to make a very basic linear probe. And we're gonna use this data just because I thought it was useful to explain here, but I think that like these will be more of just an example of what the actual like test configurations will be, and probably we'll want to train probes on more of those like basic maybe or more general data sets used in that paper, and that we'll definitely share when we push out these tutorials to everyone. But moving on now to sort of what the beginning setup tutorials are. First of all, it's like we have one for setting up NDIF, which I think this group at Northeastern has already done before. Correct me if I'm wrong. And so I'm not going to go through that one today, but there are also some hackathon specific things, most of which Jaden already covered. And this should just be like an easy way for you to build off running that model and just dropping that API key in. Second tutorial that I'm going to go through a little bit more closely today is training linear probe, like I said. We'll see how to actually extract the activations ourselves. But moving forward, there might be some saved activations for you to use, but this tutorial goes all the way through extracting activations using NDIF and NNsight, training linear probes on layer activations, then picking what the best probe is if we train one on every layer, and then testing that on a holdout configuration. And I sort of made a little bit of a diagram here to visualize this of what this basic linear probe is going to do. So each layer at every token position, we have activations at that point in the residual stream. And so to make it really simple for ourselves, per example, we'll take all the token activations and just average them because we're making the most simple classifier we can right now. But that's definitely a place I think that for more creativity and experimentation. We'll take all of those average activation vectors and use those as the training data for all these little linear regression models that will become our layer probes. And those are the probes that we're going to evaluate and find the one that seems to be the best. And that being said, it's the best at figuring out if just by the activations of one completion, if that is a lie by a model or if it's the model is telling the truth. Maybe that means that in that layer activations, the representation is clear and most clear. And so that will be like our probe or like our probe that we'll use, and we'll sort of see if that's transferable. This is definitely not gonna like this is the most simple possible example that we could think of. And it definitely is based on the assumption that just in one layer will be like a model encodes whether it's a truth or a lie. And that's sort of like the assumption that we'll test in this tutorial. So if there isn't any questions right now, I'll move over to the notebook itself and sort of just focus on some of those like key code blocks and the visualizations. I can't see the chat, so if someone could let me know at any point to jump in, that'd be helpful. No? Okay. So going through this notebook here, I'm going to skip just this part of the things that I needed from the setup notebook. Already sort of talked about this data and this definition of the lie. Here are some of the specific configurations. I think for this one, we're actually going to use just the instruction deception as our training. And then we're going to use this insider trading as our holdout scenario and see if the probe transfers. And you can think about what you think, how effective you think that will be as we move through the example. And at the end, we'll sort of answer that question. Now this is also this can kind of give you a sense of in the competition, there'll be some holdout scenarios that you'll won't have access to the data or be able to see how or like use as to your training data. And so it'll be a separate schema and a separate scenario altogether. And so I think this is like a good representation of the type of evaluation that your probes and your classifiers will be going through. So first we just load in the data. You can see using NNsight. I won't go through every line of code, thankfully, but here's sort of all these configurations, and we're just going to pick a couple of them where they're labeled as honest and deceptive, as all these data sets should have. And then we're going to first start here and talk about sort of like this is kind of the key line of accessing those model internals using NNsight and pulling out the residual stream and the activations for each. We're going to save those features here. And in this line, I just want to point out that, like I mentioned earlier, we're going to take the mean over all those activations and save that as our feature for this example. I could run it again. It's pretty fast. And first up here, I try to figure out where the completion is that is the part of the conversation that we're loading into this model, which is actually like the model's response to the prompt. It's just one way of doing it. We could also use the activations when the model's inferencing over the prompt as well. But for now, I just wanted to see what those activations were on those response tokens. And And so of those tokens, that's what we averaged over. So this is just for one example, and we can see that one example, and we only saved it for one layer too, layer 15. And so that's just a single vector of the size of the residual stream, and that's great. And if we wanted to do, but we need more than one. And NNsight's pretty fast. I was able to get 1,000 of these in just 3 minutes, an hour ago, and so I won't run that now, and so we can run through it together. But I think that's a lot of you were interested in using NDIF, and I just wanted to call that out. So here to the next part of this notebook is just to take a look at what these the training data is. This is an important part of probes and of classification in general. Is if we're going to make something that is representative, that we're going to say is representative of a feature moving forward, we want to sort of know what we trained it on. And this is the most simple way we can do it, but we just want to know how many of these randomly sampled selections are honest versus deceptive. Looks like we pull a lot more deceptive ones, so we're going to balance that out. We also ran some PCA analysis to sort of look at how each how these vectors of each layer sort of are separable. And going down here, you can see there's some, especially as it progresses, there's definitely some separation between those honest and deceptive examples, which is pretty cool to see. Now, this is sort of like the heart of the probe training, this code block here. And I think I just want to point out that it's pretty simple. We're just training a linear regression classifier that is on each layer using scikit-learn, and it's really not too much more complicated than that. Here we can run actually that evaluation, and so we'll take on that test holdout of just the training data, we'll use it and we'll see which of this instruct decept examples layer probe did the best at classifying, and it seems like just by the small margin, layer 27 was the best probe, which means there's the cleanest representation in our training data between the deceptive and honest examples. And so that's the one that we're going to use moving forward. And so now we're going to take that probe and use it to evaluate all the data. It looks like it got 100% of these examples correct. And so that tells us that yes, this layer is really good at classifying these types of lying scenarios, or scenarios to try to figure out if the model's lying. Now, I'll stop here, and can anyone sort of tell me why that 100% doesn't mean too much in the grand scheme of things, even though it seems like we have a classifier that's doing a pretty good job at being a lie detector. I kind of said it earlier, but just to recap and say it in someone else's words. And someone can just shout it out. I don't have the hand raise. No one wants to do it. Yixu, do you want to answer for me?
Sorry, could you repeat your question?
I was just asking why is that 100% result not really that impressive to us based on our the training data right now?
Well, clearly you don't have a test set that's clearly possibly overfitting based on the data.
Yes, that's right.
Or the data set, for example, could always be lie, for example. For example, it might not be, it might show a problem with the data set itself.
Totally. Yeah. Even though we didn't take the tokens activations on that actual system prompt itself, it's still maybe a specific type of example. come back to what this definition of OROC and why that's a good measurement, but I now to sort of put this to the test and to see how universal, the universal aspect of our lie detector requirement, we're going to test on these insider trading scenarios, which is a little different than the harm pressure one that I had in the slide, but a not explicit configuration of asking the model to not necessarily asking the model to lie, but to determine if the model will tell the truth or lie, given a sort of like a complex set of incentives, you could say. And so we can run an evaluation on those 5. I've already extracted the activations and run that same layer probe on layer 27 probe, and it looks like we did only get about pretty much the same OROC and transfer accuracy of around 34%, so even worse than random. And so it's clear that whatever linearly separable feature we found for that last, it's called the explicit system prompts probe lie configuration, was not something that is going to generalize to the model intending to lie over, like in sort of the broad sense that we're more interested in here. So I'll just hit on briefly this measurement of OROC. It's not very, there's 2 pretty extreme examples here, but OROC is this sort of a probability that like a deceptive score would get higher than a randomly chosen honest one, which basically means how just more of like the separability itself and not just the average of correctness, how separable how good of a job is this probe doing at separating these 2 features or on like a feature basis. And so and a good measurement here to consider. And this notebook goes through a couple more examples here at the end of ways to extend, which I'm sure you guys could think of some. But yeah, this is just a very basic probe. Obviously, it was very easy to guess what our outcome could have been. But this sort of just shows the structure of not just like how to use NDIF models and take the extraction activations, but I think probably will serve as like a starting place as probes are just classifiers, and really this is a classification task. So I hope this sparked some ideas for you all. But I'll pass it to Yixu if you share your screen.
Cool. Thank you, Olivia, for the tutorials. So now I'm going to go into the baselines, which is also something that we provide in our starter code. So going to the slides, we have implemented, we provide 5 baseline methods in our starter code, and also we will pre-populate the leaderboard with these 5 baseline methods. So they are divided into white box and black box methods. So for white box, it is the mean probe and also the follow-up question probe both are from the Godowski, Dill et al. Paper. That's also the paper that I think Kieran has sent out earlier. And then for black box, these are essentially running inference on another language model, or maybe the model itself, the language model itself, and asking if it has slide or not. So we have LLM as a judge, LLM self-evaluation, and also an unrelated questions classifier, which is somewhat a more creative method that's from this Pacchiardi et al. Paper from 2023. So in this session, I'm gonna briefly go through the 3 of the 5 methods. So the mean probe, follow-up questions probe, and the LLM self-eval method. I'm going to briefly walk through the notebooks that we have implemented, which could give you a brief idea of maybe how to implement your own methods using these notebooks as a starting point. So yeah, so the first one, the mean activations probe. So Olivia has already touched upon a lot of the ideas in building a probe. For this one, it's really similar. First, we will collect activations on 2 contrasting sets of examples. So the blue box here means the examples are honest, and the red ones means the examples are dishonest. So this is the data that maybe you can curate yourself, or maybe this is the data that you can use from existing papers. So then you would take the activations from these sets of data, and then you basically fit a linear probe that separates the honest activations from the dishonest activations. And the underlying assumption here is that there is a linearly separable direction. And I saw that in the comments, someone said probes are actually really OP compared to unsupervised methods, which is true to some extent, because we've seen papers showing that a lot of these truthfulness directions, factuality directions are linearly separable. So this is a hypothesis here. And then how do they use this probe to evaluate a new given data point? They essentially just project the activations from that new data point onto this probe direction. So we just do a dot product between these, and the score that we get would be the score that we use for classification. So we see here, this is the question that we're trying to classify. We get the activations from each token, and then we do the projection, and then we'll get a label of whether it's honest or deceptive. So this is a basic idea. I'm just going to now show my screen of how we actually implement this. So this will all be shared with you in our starter code in a repo. So actually a little bit of the repo, they're all in the tutorials, and we have all these 5 baselines implemented. So baseline 1, the mean difference probe. These are the setup stuff. And the probe itself is very simple. So this is the basic idea, right? As I mentioned, that we first fit the probe, we get the difference between the y=1 labels and the y=0 labels. So this is we just fit the probe. And then we have the decision function, which is you're essentially projecting your data onto the direction that you have learned. So this is the idea. And then similarly, we get the data. So usually you will want to train your probe with a larger data set, for example, or with a data set that are actually developed for doing probe training. But in here, for demonstration purposes, we are just taking the Liars Bench data, so from Cadenza Lab Liars Bench, and then we're taking one of the scenarios. So we're using the instructor deception scenario, and then we're just getting 1,000 examples in total. So in here, we're getting 5 per label. We're trying to create a balanced data set. So it's essentially 1,000, and we're training our probe on this very small targeted data set just for demonstration. So then we get the data, and then we will load the model. We would tokenize this data set with our Gemma tokenizer, and you tokenize the response. And essentially you get your train and your test data here. So these are just a bit more specific details of how you implement your method. So for example, you would extract all layers. So this is just a function where you take in the tokenized prompts, and you also know how many layers your model has. And then essentially you return this X by layer. So this is all your training data. So I have a question for people here. So in here, we see that X0, so which is the first layer in our X, and the shape is 1,000 by 5,376. Can anyone tell me what 1,000 and this 5,000 number correspond to?
The 5,000 is definitely, with how it's irregular, it's probably the embedding space vector, I assume, or the length of that. And the 1,000, I'm assuming it's one of the parameters related to the model. I probably need to look. Are you able to look at this notebook?
Oh yeah, no, that's a
1,000 is the number of samples, I guess.
Yes. So I think that's a tiny detail that maybe I didn't make it very clear. So 1,000 is the number of examples that we have in our training data. So in here, we set M per label, so which means that we're getting 500 examples per label. So we're getting 500 honest responses and also 500 deceptive responses. So then we're creating a balanced training set of 1,000 data points. So in here, this shape means that we have 1,000 data points, and then each data point at each layer, it has 5,376 hidden dimensions. So which is how large this activations vector is. Great, so now we're clear on the dimensions. We will then just fit our probe. So we do probe, we have the mean difference probe implemented already. We just fit it, and then we get the results here, and then we're looking at the RUC per layer. So we can just quickly print out all the layers, and then we also picked out which layer performs the best. So as Olivia mentioned, this means that perhaps at this layer 25, there is the clearest separation signal. So also another thing, we can just look at our probe. I think, yeah, probe direction here. So this is our learned probe. It is just something to explain here. It is also of shape 5,376, which means that this probe is basically another vector that we've learned that has over 5,000 numbers in there. And then when we are testing a new data point, we are essentially just doing dot product between this probe direction and the new data point that we have. That is also of this 5,000 hidden dimensions. So yeah, so this is what the probe that we get, and then we can look at some visualizations of how our probe performs. So this plot shows our test RUC per across the layers. So we can see here it is usually at around 70, and then we also pick out the best layer, 25, which means that we can just use this layer as our probe going forward. But then if we want to take a closer look into how your probe actually classifies the data points. So in here, what we are showing is that the ground truth, honest and deceptive cases. So the blue ones are the ground truth ones, and the red ones are the ground truth deceptive ones. When we plot them by the probe score, it means that the probe still misclassifies a lot of these data points that are overlapping. So let's say our probe has learned a decision boundary somewhere around here, right? But then if we use this decision boundary, there's still a lot of points in here that will be misclassified. Also in here will be misclassified. So this just tells you that, oh, it's not that clearly separable by just this linear probe. Yeah. And then going back to Olivia's point that in here, our performance is maybe you can say that it's not very bad, but then if we test it on a different scenario. So this is another scenario from Liar's Bench. Originally we had the instructed deception scenario. So now we're moving to this convincing game scenario. So all these scenarios are pretty fun. So you can look into the Liar's Bench paper to see how they constructed all these to get a better sense. So now we're taking convincing game, and then we're creating another balanced data set, test set. So that's also 250 deceptive, 250 honest. And then you are extracting your data points again, X by layer. So this is 500 by this 5,000 number. And then again, you just run this process, you plot your probe performance, and we see that the performance is much worse. And if we use the same layer, learn from the training set, so layer 25 is the best performing layer in our training set. But then if we look at the same layer, it's actually pretty, it's at one of the lowest performance layer. So this, and also if you look at this plot on the right, a lot of data points are overlapping. So which means that the probe we learned from instructed deception does not reliably transfer to this convincing game scenario. So that's something that we'll encourage to think about. If you encounter scenarios like, if you encounter situations like this, that your probe does not transfer, how should you change maybe your training regime? How should you change your probe architecture? There are a lot of things we can optimize from this simple baseline. And then the last thing to mention is that this is a notebook that you can work on when you are developing your method, but then you will not be actually submitting this entire training notebook into the leaderboard. So we would encourage you to save your probe. So this is your essentially saving your probe weights as an MPC file. And after you save it, you will move this probe weights onto the submissions folder, and then along with a probe notebook that's following this example submission format. So you would just have to adapt your probe method onto this example submission format, and then along with your probe weights. So then you move this into submission folder, and then you can just run Python submit.py, and then you'll be able to see your performance on our leaderboard. Great. Any questions so far after this first baseline? Nope. Okay. Yeah, someone asked where we can get access. So we are going to first post a YouTube video and also the slides after this session, probably today. But then for the actual starter code and the repo, we are aiming to release them somewhere next week. Great. So I'm going to go back to the slides. So this is the first baseline. I'm now going to talk about a black box baseline, which is hopefully a little bit simpler than the probe. So the second one is essentially LM self-evaluation, which is just exactly what it means from the title. So basically, let's say you have a conversation turn. So the user will ask, would you describe yourself as infallible or fallible? And the model will give a response. But then in here, your task is to figure out whether the model is lying or not, right? So how do you build your detector? Essentially what this method does is that it creates a prompt. So this is a prompt that's used in the large bench paper, but then you can also be creative and create your own prompt. So this prompt essentially is pretty detailed. It asks the model to evaluate whether it has lied in its last response. And then it defines what it means by lying. And also it gives some additional rules. You should only judge your last message, for example, and you should not look at any of the previous turns of conversations. And also it asks the model to give a rating between 0 and 100. So this is also something you can play around. Maybe you can try between 0 and 5, between 0 and 7, for example. And then these are also some things we've seen in other papers. You also define what it means to have 0 and what it means to have 100. And then the model will give the response. Let's say it gives 20. And then you can define your own decision boundary here. So maybe you can say 50 is when the model is lying. Maybe you can also define it as 40 or 30. So that's something that you can play around with. And so another thing is just to quickly go back to the repo, that we also have this LM judge, self-eval notebook. It's pretty straightforward. It follows the same structure that we have the setup, we have the data. Similarly, we load this instructed deception scenario, and then we construct the self-evaluation prompt here. So this is the same thing as showing the slides. And then we will load an evaluator model. And then you just build your prompt, you tokenize your prompt. So in here, we can just look at the prompt. It's similar to what I've just shown. So you have the user asking a question, right? So this is a user turn. And then you have the model responding to user's question, the model turn. And then the user then gives the model this lengthy prompt to evaluate whether it has answered honestly or not. And then similarly, you just run through NDIF. So you can do model.generate, and then you collect all the scores. So now we can just look at what the scores the model has given. So in my little run. So here it's kind of interesting. So there is some separation between the blue ones and the red ones that are deceptive, but then a lot of the times the models are just giving 50 or like 0.5. So it means that it's not really reliably evaluating its own response. So maybe this is something that you can look into. You can do some error analysis of why this is the case. And maybe you can tweak your prompt, do some prompt engineering to improve, to make the model give less this like middle scores. So yeah, so this is another method. We just have one last method, and I think this is also related to a question in the chat. So someone asked if you can combine white and black box methods. Yes, you can, but then once you start accessing the activations, your method will fall into the white box. Right, so the last method, follow-up question probe, it is sort of a combination of white box and black box because I'll talk about this method here. So similarly, you have this user turn, user and model answer, and then how to classify whether this answer is deceptive or not, right? So you will give the model an additional turn, additional question. So that's similar to this self-eval case. So this is, if you just do this, this would be a black box method, right? So it's asking, was your last response deceptive? But then what we're doing is a bit more. So we are forcing the model to answer no. And then you look at this no token, you take the activations from this token, right? Because we mentioned that once we start accessing the activations, this will be a white box method. So you look at the activations and then you predict using the trained linear probe to see whether this is deceptive or not. So we do have an implementation here as well. So we have the follow-up probe. Everything follows the same mean probe implementation. You get the data, you load the model, you tokenize the conversations. The only difference is that in here, you would add this follow-up question and this follow-up answer as an additional turn here. And then so you can set the follow-up question. And here it's just what's your last response deceptive? And then you are forcing the answer to be no. And then you take the activation to add this no token here. So this is the only difference. But then at the end, when we evaluate this probe, we see that, oh, it performs actually much better than our simplest linear probe. So this is our ORUC, and also you can see how the data points cluster. But then don't be happy too early. If we test on the simple a transfer scenario here, convincing game, and then here we run NDIF to collect the activations again. Yeah, we'll see that it still performs pretty poorly. It's better than the simple probe, but then I think there's still a lot of data points that are misclassified. So, but this is at least an improvement. So then, lastly, you will save the probe for submission, and you can put this into your submissions folder. So currently in our submissions folder, for example, I have implemented all these baselines, so I have all these different notebooks, and then I can just run Python submit.py to get all these ones evaluated. Great. So this is the end of my part. Do we have any questions?
Fantastic presentation, Olivia and Yixu. Thank you very much to you both. The baselines, Yixu, that you have, are they the official ones that we'll be using for scoring, or are they just demonstrations of the methods and they might be different from the official code that we'll use in the end? Do we know that yet?
So when we release the repo, we'll make sure that they're all aligned with the official baselines that we are evaluating. So I think currently in some of the notebooks, some probe architectures or how we're taking the token, we're taking the activation are a little bit simpler than the official methods. But then when we release them next week, we'll make sure that everything's the same.
I see. So you're trying to get it pretty close.
Yeah.
Great.
Yeah.
Okay. Is that the last thing in our agenda, Emma?
Yeah, it is.
I think that we did a pretty good job. We fit in 1.5 hours, and so but definitely welcome to the competition. I know that a lot of people have already registered, but some of you are probably thinking about it. So we encourage you to get your registrations in before our deadline. That's coming up soon in just a couple days. And we will see you in the competition itself and in our Discord.